Hello. So here we have a few different charge distributions. Ignore the second one for now. The top one, starting with the top one, I want to find the total energy that charge Q3 has. Okay, so we'll call that U, whatever goes green, we'll call that U3. So the great thing about energy is it's not a vector, right? That means that whatever energy 3 has, it's just whatever different kinds of energy it has, we just add those all up, and that's the total energy. So because it's a charge, and we haven't mentioned anything about the Earth or velocity or anything like that, its only energy is going to be due to these other charges, right? It may want to go towards or away from them, and that attraction has energy associated with it. So the total energy it has, I put a sum there. So the sum of the energy that U3 has is going to be equal to, well, the energy from Q1, I'll say the energy between Q1 and 3, plus the energy between Q2 and 3. Now, there is some energy association between Q1 and Q2, but that doesn't have anything to do with Q3. So this is the total energy of Q3. Alright, so let's recall in general that electric potential energy is K, one charge, times the other charge over the distance between them. Alright, so using that equation, let's continue filling this out. So this total energy is going to be K Q1 times Q3 over the distance between them, plus K Q2 Q3 over the distance between Q2 and Q3. Oops. So the distance between Q2 and Q3, I called that R2. Okay. But this one here, this other R, that's the distance between Q1 and Q3, which is right here. Okay, we're not given that, but we should be able to figure it out, right? It's just looks like a right triangle to me. So using the Pythagorean theorem, this R is the square root of 3 squared, oops, plus 4 squared, which happens to be 5. Okay, so we can plug all these numbers in, right, and get the energy. I'll go ahead and kind of partially plug in. I'll pull out the K, and we've got Q1 is -1 times Q3 is 3 over 5, plus Q2 is 2 times 3 over 4. Okay, so that's going to be equal to K times -3/5 plus 6/4. We'll want a common denominator. Let's go with 20. So multiply the top and the bottom of this by 4, and we get 12/20. Multiply the top and the bottom of this by 5, and we get, let's see, 30/20. Okay, so, and of course I should be writing these units here, but since it's an energy, I know that in the end it's going to be in joules, right? So this is going to be, so this is 30/20 plus -12/20. That makes +18/20. So +18/20 of K in joules. Alright, and of course we could look up K and plug it in, but I'd probably need a calculator at that point, so I don't want to. Okay, so that is the energy, the total energy of Q3. Alright, so there it is, fine. A couple things to note is there were negative charges. There was a negative charge. We did, in fact, plug that negative sign in, right? There are no absolute value bars in this energy equation. So you do go ahead and plug in the quantity, and if you get negative energy, that may seem a little strange, but it's okay. Just go with it, and you end up subtracting or adding accordingly. Alright, so in this next problem, as you can see, there's a pretty similar distribution. I, in fact, copied and pasted it, but I made a change, and it's that instead of having a charge here, that's just a point. So there are only 2 charges in this problem, and then 4 distances. I didn't put units on those distances, my bad. We'll say those were meters. So 4 meters away from that charge is point P. I want to find the electric potential at that point. Okay, so not to be confused, while we're being colorful here, not to be confused with electric potential energy. Electric potential is a capital V. We'll come to call that voltage at some point. And it's just K, Q over R. Okay, so pretty similar. It is also not a vector, so it's in that sense it's very nice to work with. So we're looking for the total electric potential at point P. It's just going to be the electric potential it has due to all of the different charges. So it has some potential due to Q1, and it has some potential due to Q2. So as you can see, well, you're probably seeing why I did these problems together. They're kind of similar concepts. We already know that this distance is 5. And yeah, let's continue. So this is going to be KQ1 over the distance to Q1, which is this R, plus KQ2 over the distance from P to Q2, which is R2. Okay, and we can plug in some numbers, I guess. Factor out the K again, and that's -1 over 5 plus 2 over 4. Is that right? Yes, it is. Okay, and do the common denominator again. That's negative, let's see, 4/20 plus 10/20. And so we get that the total electric potential at point P is equal to, let's see, 6/20 of K. And that's in volts. Alright, so these are similar concepts, and they're easy to confuse, so watch out. If you hear the word energy, it's definitely this top one, right? It's called electric potential energy, but they will definitely use the word energy if they're asking you, if they mean this, if they're asking you about this energy. But they can't, they will just call it electric potential for V down here. V is the electric potential. If it's a delta V, it's called the electric potential difference. But the names are similar, so watch out. So this is electric potential down at the bottom, and this is electric potential energy up at the top. So while I've got this example here, there's one more point I want to make. There is a easy association between these two. You can actually kind of just tell by looking at their equations. It is that electric potential energy of a charge, the electric potential energy of a charge, is equal to that charge times the electric potential that it has. Okay, or the electric potential at the point where it is. So that applies directly to this situation. When we had just a point sitting there, or when there was just a point, we found the electric potential at that point. You don't have to have a charge there. It's just a potential. So if there's a charge over here and a charge over here, we can find the potential at this point here. Then up here, we found the energy that this charge has. This charge is sitting at what is a vacant point in the lower problem. So because there's a charge here now, we can find the electric potential energy that this charge has because of Q1 and Q2, like we did. However, we didn't really need to do both of we didn't have to reanalyze the geometry both times. We could have just done this once and then used this red equation to calculate the other one. So let's just see if that works. So we're talking about this Q3 and who's at this point P, right? So apparently the energy of 3 is equal to its charge times the potential at the point where it is, which is this VP. Okay, well let's see if that's true. This was K times 18/20, and apparently that's equal to Q3, which is 3, times this potential, which is K times 20ths. Okay, so we can do some canceling here. K on both sides, 1 over 20 on both sides. And so 18 is indeed equal to 3 times 6. Okay, so I just wanted to relate all those equations together in one go. And there you go. So in conclusion, just watch out for the difference between electric potential energy, U, and electric potential, V. That is all.